Okay, here we are in the exercises, and I've got 4 picked out. So this is a good time for me to remind you that the best way to do these exercises is to pause the video, try to do this problem I've picked out right here, and when you think you solve it or when you get stuck, then play the video and see if you get the same thing as me. Or if you got stuck, see how far you got and then see how to finish the problem. So let's jump right in. This is number 7 in the textbook. The question says graph sine of x, which we just did over in the lecture video, and use the graph to decide whether the derivative of f of x, so that's sine of x, at 3 pi is positive or negative, and I guess we could also say or 0. That's usually what these questions will say. So in the lecture video, we did almost this exact same question, except we were looking at pi, and we graphed it in Desmos, and we looked at the slope of the tangent line. We don't need to graph this in Desmos because we know what sine looks like. Let's do a little bit of a graph here. We're just going to graph to the right of x equals 0. Let's mark pi, 2 pi, and 3 pi. That's where we're headed. So what we know about sine is it starts at 0 and it goes up to 1 and down and so on. Now I always forget which one starts at 0, sine or cosine. And what I remember is that cosine tells me the x value of a point on the unit circle. Sine tells me the y value. If I have an angle of 0, I'm at 1, 0. So cosine of 0 is 1. And sine of 0 is 0. So I start at 0. And I know that by the time my angle on the unit circle gets all the way back around to pi, that's half of the circle, my sine is 0 again. And in between, it goes up to 1 and back down. As I go from pi all the way around to 2 pi, at 2 pi, I'm back at 0. And in between, I had to go down to -1 and back up. Now, a key thing to remember is that sine is periodic with period 2 pi. That means every 2 pi, I repeat myself. So what happens between 2 pi and 3 pi? It's the same thing that happened between 0 and pi. So it goes up again and back down, and then down again and back up. So what is the derivative at 3 pi? Well, we don't know its exact value, but we can look at 3 pi, and we can imagine that we were riding this roller coaster from left to right. We went uphill and then downhill and then uphill, and then right here, where are we going? We're going downhill. And since we're going downhill, that means the derivative is negative. We don't know exactly what it is. It will turn out to be -1, but you can't tell that necessarily from the picture. So because you're going downhill, your derivative at that point is negative. At a different point, for example, if we had asked at 2 pi, well, as you're riding the roller coaster, once you get to 2 pi, you're heading uphill. So here, the derivative is positive. Here, it's 0. Here, it's negative, and so on. It changes depending on your point. Okay, hopefully that was an easy first question. Let's go on to the second one. This one says use this graph right above us to decide which is larger in each of the following pairs. So let's look at part A. Each of these parts is totally separate. So part A, the average rate of change between 0 and 2, and the average rate of change between 2 and 4. Which one's bigger? Well, let's put these on a graph. So here's 0. That's g of 0. It's the y value at 0, and g of 2. And so that means that the average rate of change is the slope of the secant line. So something like that, the slope of that line. Now the other one says between 2 and 4, so let's do 2. 2 is in the same spot, and then 4. The average rate of change is the slope of the secant line. It'll take me a little adjusting here to get this right. Something like that. So we've got this first quantity is the slope of the green line, and the second one is the slope of the yellow line, and clearly the yellow one is steeper. Green is this, yellow is that, so it's steeper. And so that means its slope is larger. The average rate of change is the slope. And so that gives us our answer for A. It's the average rate of change. I'll abbreviate. Average rate of change between x equals 2 and x equals 4. That's the larger one because the slope is steeper. Okay, part B, g of 1 or g of 4. Let me clear our drawings here. G of 1 is not anything about a derivative, and it's not anything about a slope. This is just testing that you remember what it means. It just means the value of the function at 1 versus the value of the function at 4. Well, g of 1 is here. So it's this height. It's this height, g of 1. G of 4 is this height. So which height is bigger, that one or that one? Clearly the second one. So g of 4 is bigger. Last, part C, this one is asking about derivatives. So our part A was about average rate of change. Part B was just the value of the function. Part C is about instantaneous rate of change. So let's look at let's look at x equals 2. And we don't have a second point to draw a line between. We're just drawing the tangent line at that point. So if you're on the roller coaster going uphill, once you're right here, how are you facing? Well, you're facing like this. So let's try to draw that tangent line. Something like that. Maybe it just needs a little adjustment, but that's pretty close, I think. So the slope of the tangent line, g prime of 2, equals the slope of this line. The other one is at 4. So at 4, we're here. Now, if you're riding this roller coaster and you are right here at 4, which way are you pointing? You're pointing this way. So that tangent line looks like this. Pretty close. And so g prime of 4 is the slope of the green line. And so now the question is, which line has a greater slope? And it's the green one, because the purple one is much shallower and the green one is steeper. So which of these values is bigger? It's g prime of 4. Now, a lot of the questions in this section are kind of like this, where they're not making you compute a bunch of limits. There are a few like that, but they're trying to understand just the concepts. Can you look at the picture and understand what the derivative would look like? Here's another one that's kind of like that, number 13. They give us a graph of a function f of x here, and they'd like us to label 6 points, 6 points with different properties. Now, the answer might not be unique. We'll see sometimes there could be a couple different answers. So first, for example, they want us to label a point on the curve where the derivative is negative. So derivative is negative means if you're on the roller coaster, you're pointing downhill. So let's start right here. If you're riding the roller coaster, here the derivative is positive, you're going uphill. Here the derivative is 0 because you're flat at the top. But now you're going downhill. And if you're going downhill, the derivative is negative. So here is a point that we'll label A, where the derivative is negative. Now you also could have labeled a point over here. You're also going downhill there. So there are multiple possible answers. Part B would like us to label a point where the value of the function is negative. Now be careful that you read this correct. This is not the derivative, not where the derivative is negative, where the value of the function is negative. So this is again trying to test that you can remember there's a difference between being below 0 and going downhill. So think about this. You could be, like if you're on the roller coaster right here, pretend that this is the ground, and this is one of those roller coasters that goes underground for a little bit before coming back up. If you're here, you're above ground and going uphill. So your function is positive, that's your height off the ground, but your derivative is positive because you're going uphill. If you're here at this point A, you're still above ground, so the value of your function is positive, but you're going downhill. So you can have a positive value, but a positive or negative derivative. Same thing if you're below ground. So if you're right over here, you're below ground. So this is the point B that we're going to label. You're below ground, so the value of your function is negative. Here I'm below ground and decreasing. So my function is negative and my derivative is negative. If I continued the graph and I went like this, then right here I'm going back up. So my function is negative, but my derivative is positive because I'm going uphill. Okay, I hope that made sense. On to part C. They would like us to label a point C where the derivative is largest. So where is the derivative the largest positive number? Well, let's think about what that means. A derivative of 0 is your flat. If it's small and positive, it's not very steep. It's a shallow part of the curve. the larger that slope, the larger the derivative, the steeper it is. So this is really like asking, if you're on the roller coaster, where is the curve the steepest? And this you kind of just have to eyeball. To me, it looks like this part here in the middle of this ascent up the hill is steeper than this. That's just kind of what it looks like to me. So I would say the point that we see where you're the steepest is probably somewhere right around here. So that's the largest derivative. Part D says a point where the derivative is 0, and we've talked a lot about what that means. The derivative being 0 means your tangent line has slope 0, so it's flat. So that's anywhere where you're at the top of a hill or the bottom of a hill. So let's label a couple, even though we don't need to label, it only says to label one, but we could label the top of this hill, or the top of this hill, or the bottom of that hill. At all of those points, even though like at the bottom of the hill, it's very temporarily, you're facing straight forward. You're totally flat before you go back uphill. Okay, lastly, points E and F, two different points where the derivative is about the same. So we're looking for two different points where you're either basically the same steepness up, or same steepness flat, or same steepness down, as long as you're the same. And we've already actually labeled a bunch of points like this, so we could label those 2 points, E and F, because they have the same derivative, which is 0. You could also try to find a point like here and here, where you're going downhill at the same rate, or maybe like here and, I don't know, here, where you're going uphill at the same rate, though that's a little bit harder to see. Okay, so no calculation here, just trying to understand the ideas of a derivative. It's really important, especially in these early sections about derivatives, because we're going to be dealing with derivatives for weeks and weeks and weeks now, multiple chapters of the book, that you build up this baseline foundation of knowledge of getting what a derivative does, as opposed to just trying to memorize things. If you can build this foundation of what a derivative means on a picture level, then a lot of the future chapters are going to be much easier to understand. I think we've got one more problem here. This is number 19. It says, suppose that we have a function f of x, and we only know two things. We know f of 100 equals 35, so that means the value at 100 is 35, and we know the derivative at 100 is 3. We're supposed to use this information to estimate f of 102. Okay, so we're going to use this information to get the best estimate we can given this information. And it could be wrong, because it's possible that between 100 and 102, the function does something really wacky and changes dramatically. Of course, it could always do that. But we only have this information, so we're going to get the best possible guess given this information. So let's draw what we know, and it's not too much. We know that we have some point on the function. Let's pretend that we've got some axes here. This is at an x value of 100 and a y value of 35. So this is the point, 100, comma, 35. What we know is that the derivative of this curve, we don't know the curve, we don't know what it does here or here, but we know that its derivative at this point is 3. So what that means is that if I'm riding this invisible roller coaster, I don't know what happens, but the second my car gets here, I do know a little bit which direction I'm heading. I know that I'm heading upward at a slope of about 3. So let's make a little line here, something like this. And can I make this a dashed line? Yeah, let's make it like that. So that's not saying that this is what the actual function does. It might not be a line, but I know that whatever my function does, as it passes through this point, it's kind of like parallel to this. So for example, my function could do something like this. Or my function could do something like this. Or my function could do something even weirder, like maybe this. I don't know what it does, but I know that once it passes through this point, it's kind of pointing upward at a slope of 3. So how are we going to estimate f of 102? We know our value at 100. The question is, if we're going 2 to the right, from 100 to 101 to 102, what happens to my value? And of course, I just drew a couple of different pictures for the function. We don't know which one is the real case. But with this information, the best we could possibly do is extrapolate from this information. So I don't know what my function does, but as I go from 100 to 101, 101. This line has slope 3. So if I go over 1, that means I'm going up 3. That's 35 going to 38. And if I go over by another 1, I go up another 3 to 41. So we're using our derivative at 100 to estimate what happens. And like I said, I'll reiterate this, it's possible my function does something like this, in which case my guess is an overestimation because my function is getting less and less steep as I go. Or it's possible my function does something like this. It's actually getting more steep, and so I have an underestimation. Or it could do something weirder. But this is the best guess that we can find given only knowledge of our value at 100 and your slope at 100, your derivative. So you would write this out as f of 102 is approximately f of 100, the value that I already was at 100, plus 2, because we're going from 100 to 102, times the derivative at that point. Now again, you could memorize this formula. I don't think that helps you. I think just having one more formula to memorize is tricky because you've got a lot of formulas in your head and then you have to remember which one to apply in which place. If you remember the ideas, you don't have to memorize any formula. You can just come up with the answer on the fly. You don't need to memorize things like this. But the idea is that you're starting at 35 and you're going to take 2 steps to the right, and our best guess for what happens to your height when you take a step to the right is that you go up by 3 because of our derivative there. So approximately 41 is our guess. Okay, so if you check the suggested homework, you'll see I've suggested a bunch of other problems from 2.2. This is an especially good section, like I said before, to make sure you're doing a bunch of suggested homework to make sure that you really understand the ideas. Okay, that's it for today. I'll see you next class where we'll talk about the derivative of a function in section 2.3.